This video is going to cover mesh analysis, which is in section 3.4 and 3.5 and in 3.6, and we are also going to cover some math topics since the result of today's poll says at least I should review some of the math, put it in perspective. So, mesh analysis. Well, we did nodal analysis last time, and that uses KCL, Kirchhoff's current law, and it finds unknown voltages, node voltages. So mesh analysis, also called loop analysis, uses KVL, Kirchhoff's voltage law, and finds unknown currents. So they're kind of complementary to each other. Mesh analysis is a little bit more restrictive because mesh analysis can only be used for planar circuits, and that means circuits where no branches cross over each other. So the way your book draws circuits, this circuit for example in B, anywhere like this where it's clearly that's not clear. So the book has it that this is jumping here, so the wire is jumping over here and jumping over here, and then you redraw the circuit and you can actually move this part of the circuit out to the outside. So here's the circuit redrawn here, so there's no branches that are crossing over each other. What is not clear in the way it's drawn in the book is that if there's a connection on my circuits, if there's clearly a connection, well, this one is not ambiguous. This one is ambiguous. How do I know that this wire doesn't just jump over this other wire right here? It could be a jump over and I can't tell. So you don't want to be ambiguous in the way you draw the circuit. So put dots on your circuit when there's a questionable node. But anyway, you can only use loop analysis or mesh analysis if there are no branches crossing over each other. So what defines a loop? Well, first of all, a loop cannot contain any other loops within it. So in this picture I have, this is a loop, but this out here, this on the outside, this is not a loop. So that would not be a loop. So I see two loops. The choice of your loop directions, which way you draw it, is arbitrary, but book likes to use making everything clockwise, and that's fine. It's actually nicer to be a little consistent and make everything go in one direction, either clockwise or counterclockwise. So, like when we did nodal analysis, I gave you the procedure to follow, so just like your textbook does. So here's the steps to determine mesh currents. So we are doing loop analysis to determine currents. Remember, nodal analysis is node equations which determine node voltages. So you're going to assign loop currents or mesh currents to all of the meshes, and this time you're going to apply KVL to each of the meshes. Then you'll use Ohm's law and find voltages in terms of the mesh currents. And an example will show this. And then you'll solve the simultaneous equations that you get. If there are n loops, there are n simultaneous equations. So like I said, the choice of the loop direction is arbitrary, but it's kind of nice to make them all one way. When you get ready to analyze your circuit, there is an assumed direction of current flow, the direction that you draw your loop in, because that's a loop current that you're showing. Mark your resistors. So if we're using this conventional current flow, current goes into a resistor. The potential at the input side is higher than the potential at the output side. So go ahead and mark your resistors in your circuit. It helps you with doing the accounting of the signs. So here's the first example that we're going to go over, and the book already drew in where the two loops are. But what the book doesn't do, that I like to do, is I do like to go through and put my polarity markings on. So current is going this way, so current is going in this way, so I'll put a polarity marking. Current is going this way, this way, and these polarities are given to you. Current in this loop, loop 2, is going this way, so this will be a plus, a minus, a plus, a minus, going around the loop. And over here, it's a plus and a minus. So what you have here, you only have one current here, but this one current is actually part of the current going this way, but part of the current going the other way, so it is a net current. So now let's go ahead and write the two loop equations. So over loop 1, we get, so I'm going around the loop, I hit a minus 15 first, plus 5I1, plus 10I1, but I1 is going this way and I2 is going the other way, so it subtracts minus 10I2, and then I get a plus 10 volts, again, plus 10 equals 0. So I can rewrite that and simplify it, and I will get 3I1 minus 2I2 equals 1. So that's for loop 1. For loop 2, or mesh 2, I'm going to go around the loop. I don't care where I start, but I think I'll start right here. So it's I2, it's the loop. I2, I just noticed what your book did. They have capital I's here and little i's for the loop. Just ignore these. I'm calling them all. This is an all DC circuit, so I'm using capital I's. So I have I2 times 6 ohms, because that's Ohm's law, plus I2 times 4 ohms, minus 10 volts, plus 10 ohms times I2. So I2 is going this way, but other current is subtracting, going the other direction. So I must have a minus I1 10 equals 0. So I rearrange those terms. I'll get I2 equals 2I2 minus 1. If I was using the book, it was 3I1 minus 2I2 equals 1, and I2 equals 2 I1 equals 2I2 minus 1, or I1 minus 2I2 equals minus 1. So at this point, I have two equations and two unknowns. The problem is to solve it, and I can do it by process of elimination. 3I, well, I'm just going to rewrite it, minus 2I2 equals 1, and then I1 minus 2I2 equals minus 1. I could solve for I1 and substitute it back in here. Solve for I1 in this equation, substitute it back up here. I'm a little bit fond of doing the adding or subtracting the two equations. So I'm going to subtract the second equation from the first, and I'll get 2I1. This one minus this one is 0, and 1 minus minus 1 is 1 plus 1 is 2. I1 then equals 1 amp. And then, of course, I can go back here, use that equation, and I1 minus 2 I2 equals minus 1. So 1, you guys can do the math, I'm sure. So I2 also equals 1 amp. Turns out that this current right here, which is I1 minus I2, turns out that that current is actually 0. So it just so happens that this in this particular circuit, there's no current in that center branch. So this was process of elimination. Elimination works pretty good for a 2x2 matrix. You could also use Cramer's rule on that. So if I were going to use Cramer's rule, I would take these two equations right here and write them in matrix form, which would be, oops, every now and then my hand makes this move, which would be 3 minus 2 minus 1, 2. So now I've written it in matrix form so I can use Cramer's rule. So talking with some of the students today, not everybody has heard of Cramer's rule until today. So I'm going to just point out that this is exactly the same as writing 3i1 minus 2i2 equals 1. That was one equation, and the other equation was, okay, minus i1 plus 2i2 equals 1. So these were the two equations that I just had on the previous slide, and I've now written it in matrix form. And so I'm doing a matrix. This is a 2x2 matrix right here. This is a, it's rows by columns. So there are 2 rows. So this is a 2x1 column matrix, also called a vector. And this one's also a 2x1 column matrix or vector. So if you are multiplying this matrix times this vector, you do row times column. So the row 1 is 3. So you're going to do row times column, and it will equal this value. So 3 times I1, this times this, plus this times this, plus minus 2 times I2 equals 1. So that's one equation, and then the other equation you get from here, this row times this column equals that value. So that one would be minus 1 I1 plus 2 I2 equals 1 right here. So this matrix form is exactly equivalent to writing these two equations out. And now I can go ahead and apply Cramer's rule. So the first thing is to find the determinant of the coefficient matrix, which this is the coefficient matrix right here. So I find the determinant of that, 3 minus 2 minus 1, 2. So it's this times this minus this times this. And you'll get 6 minus 2, which will equal 4. And then if I want to find my unknowns, unknown number 1 is found by taking this column and substituting it into the first column. So 1, 1 is going to be substituted in that first column. This column will stay the same, 2 minus 2, 2, and divide it by the determinant of the coefficient matrix. And that will give you, actually this is, sorry, this part right here is, this part here is del 1. And so it's divided by delta there. And that will give you I1 by definition. So I do this matrix, and I get this times this is 2, minus this times this, so it's 2 plus 2, which is 4, divided by 4, and the answer is 1. So I1 is 1, just like we got before. I2 is this determinant 2 over the original determinant. So now I go back here and I substitute the output column vector for the second column here. So 1, 1 gets substituted into here, divided by determinant, divided by 4. This times this minus this times this is 3. minus minus 1 is a 4 over a 4, and you get the current as being 1 also. So there's a third method to solve. The first one was elimination. The second one was using Cramer's rule. And the third method is some matrix methods, which I'm going to go over at the end of this presentation. The matrix methods are best for solving if you had something like 5 equations and 5 unknowns, which is what I'm going to do. And I'm not going to do process of elimination for 5 equations and 5 unknowns. So now, so we had a special case when we were doing nodal analysis when there were voltage sources involved. So now, similarly, now we're doing mesh or loop analysis, and there's a special case when there's a current source involved because you don't know the voltage across a current source. So the first case is case 1. A current source exists in only one loop. So if I go over here and look at this, there is a current source, but it is only in this loop. It is not shared by this loop over here. So it turns out it's kind of like a constraint like we had before, and we can solve the problem. Let's write our loop equations. At loop 1 we have minus 10 plus 4i1 plus 6i1, and I'm going minus i2, correct, equals 0. And for loop 2 we have 5, because we already, it's minus 5, going in the wrong direction, minus 5 plus i2 times 6 minus I1 times 6 plus, oh, well, gosh, I already know what this current is right here. I2 is 5. Well, maybe I should just say that right from the start. Oh well, we'll finish it. Plus 3 I2 equals 0. But we can see right now, because this part we already have what the current is, I2 equals 5 amps. So I've already solved I2. I can go back and solve I1. So this is actually the simpler problem. So the second special case occurs when the current source is in there and it is shared by two loops, and in this case you create a super mesh. Remember when we did nodal analysis, we created a super node. So this time we're going to create a super mesh or a super loop. So here's the example. It's actually a pretty good example, I think. So we have a current source. We have a current source in this branch right here, and this branch is shared by this loop and this loop, or in other words, this current source is shared by more than one loop. So what you have to do is call this a super loop. And in a way, I sort of like the way the book did this. The super loop is like comes out of the circuit essentially, and you do the analysis by saying it's kind of like you divided the circuit in half. I1 exists here and here, and I2 exists on this half of the circuit. And so then you have to write the loop equation that way. So when I do that, going around now this loop, I have minus 20 plus 6I1 plus 10I2 plus 4I2 equals 0. So that's 6I1 plus 14I2 equals 20. So that's a nice equation right there. But now, in order to solve it, I actually am going to actually apply Kirchhoff's current law to node 0 in the figure. So this is where it's a little bit tricky. So here's node 0 in the figure, and when I do that, I have I2 equals I1 plus 6. So that's what's happening right here. This goes in, this is out and out, and so I get a second equation here, like a constraint equation. So now I have my two equations and my two unknowns, and I can choose my method to solve this equation. This problem that they had next in your textbook was a little tricky, actually, how you look at it. So going back to my definitions, this is a current source that's shared between this loop and this loop. So therefore, I would write a super loop right here. But then I have another current source that's shared between this loop and this loop. So all of this is shared, and this whole giant part right here becomes the super node. And so when I write the equations, I'm going to write an equation for one big loop here. So I can go ahead and do that. And so remember, I1 is in this component, I3 is in this component, I4 is here. I have something going on here. So I'm back in this loop, so I have an I3, and I'm back in this loop, so I have an I2. And that's the way you would write the equation. So going around, I like putting my signs on just to help me keep track. This is going this way, so this is this way. Okay, so I put my signs on. I'm going to go around the loop. I'm going to start right here. 2I1 plus 4I3 plus 8I3 minus I4 plus 6I2 equals 0. That looks good. I can simplify that down a little bit, so I get I1 plus 3I2 plus 6I3. Okay, so now I have to deal with these current sources that are over here. So I write KCL. Use KCL within that super loop, super mesh. I'm going to do a KCL right here. So this current goes in, this is out, and this is out. So I do that, and I have I2 equals I1 plus 5. I can do the same thing at this node right here. This is at P, this is at Q, KCL again, and I will get I2 equals I3 plus ins, yeah, outs. I3 plus 3I0, and where is I0 in here? I0 is defined as this current, so I0 is minus I4. So I can put that in there. Okay, so then at this point, I think we have all that we need to solve this problem. Oh no, I didn't write my other loop equation here, so I don't have it. I have too many unknowns still. So I have to write for this loop right here, which is 2I4 plus 10, this plus 10 plus 8 I4 minus minus I3 equals 0. So I have this equation, 2, 3, 4, and I have 1, 2, 3, 4 loops, and I have 1, 2, 3, 4 equations. So this one is a 4 equations and 4 unknowns. Ooh, how would you solve for that? Okay, so let's talk a little bit about the math. So Nodal analysis applies KCL, and mesh or loop analysis applies KVL. But these problems, they always end up being a case of solving simultaneous equations every single time. So in section 3.6, there were examples, which is the section we just finished, where, no, it's the one we're doing right now. They show these examples where you can write down these equations by inspection by just applying the rules. I frankly am not quite, I could do it if I did it all the time, but I don't do it all the time, so I just prefer to apply the rules and write down the equations. So I did for this problem right here. I actually applied my nodal analysis on this equation, so it's a nodal analysis. At node 1 I have this current going in. I'm going to make some definitions. Let's put current this way, this current this way, and you can see current is this way. So I1 equals the current going out. So the current going out right here is V1 over resistor 1. So it's actually V1, the current going out is V1 divided by R1. But 1 over R1 is the conductance, G1. So I can do this whole problem in conductance. So then I write my second node equation for this spot right here, and instead of saying 1 over R's, I just switch everything to conductance, and then I get my matrix equation here. So it turns out that every time you apply nodal analysis, you get some kind of a matrix here of conductances. And it's always a conductance matrix times your unknown voltage equals the currents that you're going to solve for. So it's always going to have that form when you're in nodal analysis. And this, how big this problem is depending on, I have two nodes here, I have two equations, and I have two unknowns. So if I had 3 nodes to solve for, you're solving for the node voltages, then I'd have 3 unknowns and 3 equations. If you don't, you had done something wrong. Similarly, if you were doing mesh analysis, if you have 3 loops, then you have 3 equations and you have 3 unknown loops to find. So that's actually kind of worth summarizing. Or do I have that on the next slide? Yes, well, it's kind of an example. Here's somewhere where I'm applying a mesh analysis or a loop analysis. There are 2 loops, so I will have 2 equations and 2 unknowns, but when I write my loop equations, they always end up being in the form of known v's, and I times R1, I times R2, and my i's are the unknowns. So I always end up with a coefficient matrix that's resistances, and I always end up with a vector of my unknown currents, and it always ends up being a vector of my known voltages in the circuit. So this is what happens when you do mesh or loop analysis. So 2 loops, 2 unknown equations, 2 unknowns, and you need 2 equations. Even in the special cases. Mesh node analysis, number of nodes equals number of unknown voltages, equals number of equations, simultaneous equations that you have to solve. And so nodal analysis will always be in the form of a G matrix with an unknown voltage vector equals your known currents. Mesh or loop analysis is always going to be in the form of a resistance matrix, my unknown currents, and my known voltages. So in either case, it's always a bunch of equations and a bunch of unknowns, 5 equations, 5 unknowns. So I wanted to go over for a moment about the math, the different math methods that you can apply to these problems. Make this a little bit bigger. That looks better. Okay, so the first one that you probably learned in even algebra was process of elimination. That works pretty good if you have two unknowns. You can even do it with three unknowns, but although it's tedious, right? So if you have two unknowns, process of elimination works pretty good, especially if the numbers are nice in the equation. If you have two or three unknowns, you can apply this process of Cramer's rule. It's a little uglier with three unknowns. We did it in the last video, but you can apply Cramer's rule and you can find your two or three unknowns. So two unknowns, you would be having a 2 by 2 matrix of coefficients. Three unknowns would be a 3 by 3 matrix of coefficients. And then as the problem grows, beyond 3 by 3 matrix, it gets really, really ugly. And in that case, you should resort to matrix inversion techniques, which are from linear algebra. And when you are a junior or a senior at your university, you will take a course in linear algebra that will go in a lot more depth. But anyway, if you get too many loops or too many nodes, you're going to have to resort to some computational way to find your unknowns. So you can do it by hand, but it gets very, very tedious, extremely tedious. But it's best to use your calculator or a math program. So notice that I have over here an arrow. So as I'm going down my list of your tools, math tools that you can use, I'm getting an increasingly large number of unknowns. 2 by 2, do this. 2 by 2 or 3 by 3, three unknowns, do Cramer's method. More than that, I would resort to a math program. So let's do some examples. Here is a 2 by 2 matrix. Well, this can be represented as a 2 by 2 matrix just to show you. It would be a 2, 3, minus 2, 6. And my vector of unknowns is right there. And it equals 4, 1. So I can write it in matrix notation. This is often written as an A, and this is a vector X. Bad choice. Equals a B. So it's also written that way. If it was typed up, these would be bold letters, but I can't type on here very well, so I'm handwriting, so then it's okay to put these brackets around it. So process of elimination, I personally would look at this and say, I'm just going to add these two equations up. This is a 0 plus 9y equals 5, y equals 5 over 9. I go back and substitute it in one of these equations, minus 2x plus 6, 5 over 9 equals 1. I didn't solve this in advance, so here I am doing it on the fly. Equals 1. Oh! Anyway, you get the idea. You can finish the math. I'm not going to... Okay, this is 9 over 9 minus 30. So that would be... So that would be the answer. So that's process of elimination. Many ways to do it. Works pretty good if you have a 2 by 2 matrix, coefficient matrix. So works pretty good for that. 3 by 3, it gets kind of ugly to do elimination or substitution methods. So here's a 3 by 3 example. Here's 3 equations and 3 unknowns. I can write it in matrix form. So you see that I'm taking the coefficients of the variables, and I put it in this matrix A. Here's my vector of unknowns, and here's the right-hand side of the equation. So there I typed it up in advance, and you can see it written in matrix notation over here to the right. So how would you solve it in Cramer's rule? First you find the determinant of the coefficient matrix. So these are the coefficients of the variable. It's this times this times this plus this times this times plus times this. Sorry again. This number, this number, this number plus this number times this number times this number plus this number times this number times this number minus, and then you go back and you do the minus direction. So there it is written out. You can trace it through and you find the determinant of the coefficient matrix. This is still tedious to me. Then you find these other determinants so that you can find the final answer. So determinant 1 means you take, this is for the you're going to need this to find the unknown of the first unknown. What you do is you take the column, you take this output column that's right here, and you substitute it into this output column right here. You substitute it into that column right there to find the first delta 1 determinant. So that's what I did. I substituted the 50, 0, 0 in the first column, found the determinant of it, and got a value. Did the same thing by substituting 50 in the second column. So I get delta 2, find a determinant, voila. Same thing for delta 3, which I'll need for the third unknown. Substitute that output column vector in the third column, find the determinant. Then finally you get your unknowns by doing this division. So there's the determinant delta 1 divided by the determinant of the coefficient matrix, and then you get the unknown x1. And you can do the same thing for x2 and x3. You can even use this method to go to a 4x4 matrix, but it gets, if this process wasn't ugly enough, you'll find out it gets really ugly and complicated, and you'll have to find these things called minors, and it's just a great big numerical housekeeping problem. So at this point it's better to use matrix methods. So the first thing you do when you want to, I'm going to do a little background on the matrix method, is write your matrices in matrix form. So I did that right here. So remember this could be, this is your coefficient matrix right here. It could be a 3x3, a 4x4, a 5x5. Right now I'm going to do an example. Actually, I'm going to do an example with a 5x5 matrix to show you the power of this. The x vector, this is the vector of your unknowns. And the example I'm going to do, it's going to be a 5. And then the b vector is also going to, has to match. It will be a 5x1. And so then you solve for the unknowns. The unknowns are this x vector right here. These are the unknowns. And the way you do that, it sort of looks like algebra, but it's not quite. You multiply both sides by the inverse of A. So inverse A times A equals inverse B times B. Now, unlike algebra, this order matters. You have to have these in the same order. So if you pre-multiply by the inverse of A on the left side, you have to pre-multiply by the inverse of A on the right side. And so when I do that, this and this, I won't say cancels out, but it creates what's called the identity matrix, which is like a 1. But it's a matrix of that's 1. And you get the unknown vector, the x vector isolated, and you have an answer for that. X equals A inverse B. Now finding the inverse, this inverse is not a very pretty or nice process. Involves determinants. Just lo and behold, you have determinants again. But you can find the inverse of a matrix, and the inverse of a matrix times the matrix will come out to be the identity matrix, which for my 5x5 problem ends up looking like this. So that's the identity matrix, and when you multiply that times x1, x2, x3, x4, 4, x5, when you multiply that out, you will get, let's do it, row 1 times column 1 should give me the first value that's over here. Row 1 times column 1, this times this, plus this times this, plus this times this, plus this times this, that's an x4, plus this times this. And guess what? You'll get just x1 out here. Row 1 times column 2, or row 2 times column 2. So 0 times this, 1 times this, 0 times this, and you'll get x2 back. So, etc. So if you look right here, I say x equals, and I will get a column vector of what x equals. x1, x2, x3 will equal some kind of a column vectors of numbers. 5, 3, 1, whatever it is. Okay. Best by example at this point. Examples are always good. Here is my example circuit. So, kind of ugly. I see 1, 2, 3, 4, 5 loops if I'm going to do a loop analysis. And 5 loops means 5 unknown currents, I1 through I5. And it means 5 equations and 5 unknowns. I personally am not good enough. Well, I make mistakes if I try to do it by inspection, but you can get good at this and do it by inspection. So, for example, going around loop 1, I go around loop 1, I put all my signs on for good housekeeping. So, loop 1, this is actually just a straightforward problem, minus 4 plus 2i1, so 2i1 minus i2. Plus 5i1 plus 2i1 minus i3, and there's loop 1. And I go do the same thing for loop 2, loop 2, loop 3, loop 4, loop 5, and in the end I'll have 5 equations and 5 unknowns, and I can put it in matrix form like that, and it will look like that. So I write my 5 equations and my 5 unknowns. Keep in mind I can recover them back by doing row 1 times column 1 equals this value. For example, 9i1 minus 2i2 minus 2i3 plus 0i4 plus 0i5 equals 4. There's my first equation. I can do it for the second equation. Row 2 times this column equals this number, and I can get my 5 equations back. So 5 equations and 1 unknowns. That sounds like an ugly, terrible problem to do. So I would rather use my programmable calculator or my nice math program. So I'm going to pick my nice math program. I already entered A because I made a mistake first. There's my mistake. I already entered A. There's the A matrix right there. And I forgot what B was. B is 4, 6, minus 6. B equals matrix 4 space 6 space minus 6, 0 and minus 6. 0 and minus 6. There's a matrix. Now, it is a row vector right now, and I want it to be a column vector. And how you do that in MATLAB is to put that mark there, and it will become a column vector. So there it is. It's a column vector. So what I just said, and to solve this equation, I need this. I need that. Oh, it's so hard to draw straight lines for me on this drawing board. I1, I2, I3, I4, I5 equals A inverse B. This is B, this is A, and I need to find inverse A. back in my MATLAB, I'm going to say, actually all I'm going to say is inverse A times B, and this should give me the answer. And there's the answer. All the 5 unknown currents all came out because inverse A times B gives me the 5 unknown currents. Now, I'm using MATLAB because I know UH Manoa and many engineering schools use MATLAB. You can use a math program of your choice, and most people's nice scientific programmable calculator can also do the same thing. So take your pick. I will continue to use MATLAB, and you can buy MATLAB for $50 from mathworks.com. You get the student copy. I also have MATLAB on one of the computers at Kauai Community College. So students, if you're here, ask me. I'll show you which computer it's on. So, okay. So if you're going to do something bigger than a 3x3 matrix, I suggest you use some kind of a math program to find your answers. So I actually put my answers up there. That concludes this lecture, actually. It's 8 o'clock. I need to go home and eat dinner.